Most electronics engineers think design is the hard part. However, in 31 years, I've seen debugging destroy far more time. When a circuit doesn't behave as expected and you don't approach it in a systematic way, the weeks can disappear very quickly. In this video, I'll show you a system for debugging that you can use on many different systems, and I'll show you how to apply it to a high-performance LC filter. Let's get started. So 30 years ago I was working on this PCB. As you can see, a lot of experimenting was done on this board. This filter was a crucial part of the Westerbork Synthesis radio telescope, and 2048 of these had to be made with 8 different bandwidths. So this first prototype did not behave as it should, and I was completely in the dark and had no idea where to start. Luckily, I was saved by a retired engineer from the company. Let's take a look at this filter in a bit more detail. What you see here is the schematic. This is a 9th order elliptical LC low-pass filter with a frequency of 30 MHz. You can also see the layout that looks very identical to the schematic. The PCB is a 1.6 mm thick 2-layer design. The bottom layer contains a ground plane, and each ground connection has a via to that plane. And here's the problem with it. The yellow trace shows what the simulated result looks like, and the purple trace shows the measurement of this PCB. There are some huge differences as indicated by the red arrow. So if you have no idea where the differences come from, where do you begin? So there are multiple debugging approaches. The one I want to show you today works like this. You start with a very small part of the system and see if that works as expected. Then you keep adding blocks to see when things break down. At this point, you try to understand what causes that breakdown. So I'm talking about blocks here because this method also works really well for complicated systems like a spectrum analyzer, for instance. In this case, our blocks are passive components, capacitors and inductors. So you'll start with just a single passive component, compare to simulation, and then see if there's a big difference. Then you add the second component and compare again until you hit a big difference. When you hit a big difference, you start the debugging process to try and find out what caused it and how to fix it. When you have, you continue adding more blocks to the system. In this way, the process is very controlled and you learn which parts of your circuit work and which parts don't, and which parts are interacting with each other. Let's see this process in practice. What you would normally do is modifying the actual board you have by drilling extra vias, rotating components, etc. etc. But a dedicated board is more reproducible for demonstration purposes like this. The upper picture shows the board without components. The lower picture shows the starting point for debugging. Only a single inductor is placed and the rest of the filter is shorted using 0 ohm resistors. So now you understand the approach, let me briefly show you the measurement setup that I'll be using. A Libre VNA is used as a signal generator, and the Signalhound SA44B spectrum analyzer is used to measure the signals. The advantage of using two instruments like this is the huge isolation between them. This allows for measuring filter suppression up to 140 decibels. If you used the Libre VNA itself, you'd be limited to something like 95 decibels, which is not enough in our case. I've also added a 6 dB attenuator on each side of the filter to make sure both sides of the filter see 50 ohms. So bad matching cannot influence the result. The setup is controlled by a Python program. With everything in place now, let's look at the first debugging step with just a single inductor placed on the PCB. The schematic shows the simulation model. A very basic model for the 330 nanohenry inductor is used. It has a 1.3 ohm DC resistance and the resonance frequency is 600 MHz, which is created with the 230 femtofarad capacitor. This is not perfect as there will be more second order losses, but good enough to start with and for this purpose. And as you can see, the simulation is very close to the measurements. So this works as intended. Let's look at the next one. So a 100 picofarad capacitor is added to the circuit, and again, simulation and measurements are very close. There is a small difference, but nothing shocking as the component models are not perfect. Let's add a 4.7 picofarad capacitor across the inductor to create an LC resonator. You can see the dip this creates as the LC resonator causes a high impedance between the in and output at its resonance frequency. It's supposed to resonate at 128 MHz, and that's pretty close. Still, everything behaves as it should. The dip is not as deep as in the simulation, but that is normal since real-life components usually have a bit more losses than the simple models used here. We are looking for bigger errors. Let's add another capacitor, and this one is going to make things interesting. So a 180 picofarad capacitor was added at the output, and look what happens. Suddenly there is a huge difference between the simulation and the measurements. The dip is almost completely gone. Now this is where debugging becomes challenging. You have to come up with a logical reason why this is happening. This step requires some imagination, creativity, and logical thinking. That's why this is the most difficult part of debugging. If you can't find the logical cause quickly, ask a colleague. Someone else often sees things from a completely different perspective, and that can save you hours or even days. I've seen many engineers struggle for days because they were afraid asking for help would make them look incompetent. The reality is that even the best engineers get stuck every now and then, so don't hesitate to ask for help when you need it. Now, with that out of the way, let's see what's going on here. Adding that capacitor ruined the suppression of the resonator. So the signal must be leaking from the in to the output somehow, and it has to do with that capacitor. In this image you see what is going on. The signal is applied to the path from left to right, and part of that current flows through the capacitor on the top layer, indicated with the red lines. The current then moves to the bottom layer using the vias and goes back under the current on the top layer. This is shown with the yellow lines. Forward and return currents always want to move as close to each other as possible. I have proof of that in another video on my channel. Since the bottom is 1.6 millimeters below the top, this creates two 1.6 millimeter high loops that act like inductors with a single winding. And they're looking at each other. Each loop generates electromagnetic field lines which overlap. They're shown in white and purple. So this is a transformer between the in and output of the filter, explaining the leak. So now we have a theory, but how do we prove it? Let's move that capacitor to see if it solves the issue. So this is the new capacitor position, and look at that, the dip is back. But now we have a different issue. The dip has moved 29 MHz down. So we're right back to debugging mode again, because there seems to be a second effect going on here. Here you see the theory you'd have to come up with. The current moving to and from the new capacitor location creates a loop that interacts with the SMD inductor. The field lines of the inductor are shown in purple and the field lines of the current in white. You can clearly see they overlap. This effect is very large, as the inductance of the SMD inductor has to virtually increase by around 60% to reduce the resonance by 29 MHz. So how to fix this? Well, try and come up with smarter positions for this capacitor to deal with it. Now to do that you'll have to drill two new vias, because you want the ground terminal of that capacitor to directly connect to the ground plane, so the current does not have to travel further to the nearest via that's already in the PCB. You always want to keep current loops as short as possible. So here you see option 1 for that capacitor position. The capacitor is in its original location but rotated. This reduces the coupling between the current loops. The dip frequency has now moved up a bit instead of down, so this position virtually decreases the SMD inductor value a bit. And you can see that it works. The dip is deeper, but still not very good. The reason it's not perfect is that the field lines from the two loops still see each other a bit, as you can see here. You can pause the video if you want to study this a bit longer. Let's try another position for this capacitor. Now this one starts to behave a lot better. It's not perfect, but it's the best we've got up till now. The input and output capacitor loops are now further apart. That helps to reduce the coupling. Here you can see a rough drawing of where the field lines are going now. The field lines from the SMD inductor and the input capacitor do see each other. However, in one of the previous experiments earlier in this video, the resonance frequency is not altered by these two loops seeing each other, which is a bit surprising. The other interactions of fields is now reduced a lot, either by distance or by being 90 degrees with respect to each other. If field lines are at 90 degrees, they will not interact. It's good to understand that this way of analyzing is quite crude. Reality is a bit more complex than this, but it's good enough to guide your experiments and find a solution. So we understand a little bit what's going on now, but it's not perfect yet. So what do you do now? The main issue is the distance between the top layer and the ground plane. This height creates current loops with a large physical loop size. If we could reduce that loop size, all coupling effects should also be reduced. This is why I always tell my students to use multi-layer boards for better RF and EMC performance. If you use a 4-layer board for instance, the ground plane is just 0.2 millimeters below the top layer. This makes the surface area of the current loops 8 times smaller compared to a 2-layer with a 1.6 millimeter board. So, does this work in practice? Let's find out. So this red PCB is a 4-layer with this preferred layout, and wow, look at that! Simulation and measurement are nearly on top of each other. The layout is a bit different than we saw before, but because of those 8 times smaller loops, that hardly has an effect anymore. Another way to improve the situation is via stitching. This creates ground walls inside the PCB, improving the situation. I've made a PCB for that as well. And here you can see what that does. The layout of the 3 components is very equal to the 4-layer board you just saw. It's not as good as the 4-layer, but it definitely is better than without the stitching. The current loop sizes are 8 times bigger again, but the stitching compensates for a lot of that. In the PCB image on the right top, you can see exactly where all the vias are. They're also under the inductor. So you've seen this type of debugging in practice now. For me, there is one absolutely crucial rule to make this kind of debugging possible. I've never seen this rule broken in over 30 years, so what is that rule? There is always a logical reason for what you're seeing. The nice thing about electronics is that it's about physics. It follows the rules of nature and these cannot be broken. For me, this realization is critical, because as soon as I started believing that, I knew a cause could always be found. I did not notice when I started out in electronics, and whenever I faced a situation like this, I'd get really scared and did not know what to do. After realizing this rule is true, I learned that from a colleague, it was just about systematically finding the mechanism behind what I was seeing. This made me feel a lot more confident and also made the process a lot more enjoyable. It also really reduced the time to find the root cause. One of the real problems is that this stuff is not taught in university, so when you start out, you're really thrown in the deep end. At least, that's how I felt. If you want to learn a lot more about the things that university does not tell you, I have a free 1-hour mini course that goes a lot deeper into the problems with this filter and the fundamental mechanisms. These mechanisms are the cause that your simulations can look perfect, but the actual boards fail. The great news is that preventing those mechanisms is actually ridiculously simple. You only have to apply a few simple rules and you'll be able to prevent 95% of these issues. If you want to learn more about these simple rules, you can watch the mini course. Link is in the description and the pinned comment on the top. See you next time.